addressing protocol, the speed and timing of delivery, message size, and confirmation of acknowledgement, etc. So let's go through those in detail. The addressing protocol in a network communication defines how the sender identifies themselves and how the sender identifies the intended receiver of the message. In an electronic group chat, for example, the sender is always identified. We always know who's sending a message. And if the sender wants to direct a particular message to one particular person in a group chat room, they have to name them so everyone knows the message is directed to that person. Network protocols take care of such things in network communications, addressing the sender and the receiver. Then the speed and timing of delivery is also something network protocols are in charge of. They're in charge of managing the speed and the timing of the communication to control when can devices send messages and how fast can they transmit these messages so the network can properly handle the communication and for the receiver to be able to process them as well. Network protocols also define the message size, how much information can be sent in one go. This is what we refer to when we talk about the message size. We need to define how much information can we send so communication resources can be fairly shared among all devices in the network. Sometimes this means that messages have to be broken down into smaller chunks so to comply with the message size defined by the network protocol. Going back to our chat room to understand message sizing a little bit better, it's an unspoken protocol that no one person should hog the room by sending long paragraphs one after the other and not giving chances for others to participate. So people usually in a chat room will send 2 lines, 3 lines at a time and give turns to others. So this is the same or relates to the message size in a network communication. Devices, we define a message size so devices do not hog the network for a long time, sending long messages. Protocols also define the mechanisms for acknowledgement. In network communications, the sender sometimes needs to know when the message and if the message has been successfully received. This is what we call confirmation of acknowledgement. And there is also a message timeout defined by certain protocols. How long or the amount of time that needs to pass before considering a message lost if an acknowledgement hasn't been received. So last but not least, network protocols are in charge of defining the rules of encapsulation. And encapsulation refers to the headers we need to place before the message to include protocol information. Let's use a written letter as an example here. When we send a written letter, protocol dictates that for the letter to be handled properly by the postal service, we must include sender and receiver information on the envelope. We have to write down the sender's name and the address, as well as the recipient name and the address on the outside of the envelope carrying the letter. In network communications, encapsulation fulfills a similar function as the envelope. Headers are placed before the message to include things like addressing information, who's sending the message and who is intended for, sequencing numbers in cases where messages have been broken down into multiple smaller messages. Headers also typically include a numerical value for the receiving end to use as a way to validate the fidelity of the information received. And these are just some of the things that a header can include. In future lectures, as we go over the specific network protocols, we will learn the specific header information for each of them. Now, as you can imagine, the process for sending and receiving messages through a network is a complex one. And as such, we need multiple different protocols managing the many different aspects of this complex process. So in order to simplify things, we've broken down the communication process in different layers. And at each layer, we define layer-specific network protocols. The TCP/IP model is a suite of network protocols, sometimes referred to as the Internet model. This model defines and describes the functions and tasks performed by devices in a network, breaking down the communication process into 4 layers: the application layer, the transport layer, the internet layer, and the network access layer. A little bit of history here. This model was developed by the United States Department of Defense in the early 70s. The model evolved from the ARPANET, which is one of the very first wide area networks and considered the predecessor of the internet. Nowadays, TCP/IP networks are the most common type of communication networks. Another important fact about TCP/IP is that it defines an open standard, meaning that it's not reserved for any one company or vendor to use or implement. Any vendor can implement the functions defined by the TCP layered model in the devices they manufacture. So we said before that the model defines 4 layers or 4 areas of functionality in the end-to-end communication process. So the top one, as you can see there, is the application layer. The application layer protocols govern the rules that software developers need to follow to produce applications that can actually run on networks or on TCP networks, TCP/IP networks, to be more specific. For example, DNS, the domain name service, is an application layer protocol. This protocol defines the standard structure of name resolution queries. So how to translate an URL or a hostname into an IP address. And please know the word standard here. The fact that the DNS protocol is a standard TCP/IP protocol means that an Apple client, a Mac computer, for example, can query a Microsoft DNS server to resolve a name, and there is no compatibility issues. So going from the top down, we have now the transport layer. The transport layer receives the information from the application layer and prepares this information for transmission over the lower layers of the networks. It will perform tasks such as breaking down messages into smaller segments that can be handled by the lower layers. And it will implement mechanisms to be sure or to make sure that these pieces are properly put back together at the receiving end. Think about the transport layer as the shipping department packaging a single item into multiple packets so they can fit into the courier specifications. Multiple pieces have to be placed into different boxes, and each box has to be numbered and identified so the receiver knows all the boxes belong to the same item and they can put it back together. So the TCP model defines 2 standard protocols in the transport layer, TCP and UDP, and these protocols define the rules of segmentation and numbering of segments, among other things. We will look at these protocols in detail in future lectures. So what are the benefits of using a layered communication model of standard protocols? Well, firstly, the fact that we've broken down the process into multiple layers assists protocol design. We have defined smaller areas of functionality with specific tasks that need to be performed at each layer. And designing and developing protocols that only look after a smaller set of tasks is easier than developing a protocol that needs to consider and manage all aspects of communications. Also, the fact that protocols defined by the model are standard fosters competition. If we have protocols that standardize communication tasks, that means that multiple vendors can manufacture devices that perform the same set of tasks. Take router devices, for example. We have Cisco routers, data link routers, Netgear routers, etc. They all perform the same set of communication tasks in pretty much the same way because they follow standard protocols. Then it's really left to the consumer to decide what vendor to go with. Because regardless of the vendor they go with, standard protocols will allow these devices to communicate with other devices from different vendors in their network or in other networks they need to communicate with. Another very significant benefit is that having a layered architecture means that changes at one layer do not affect other layers. For example, if we want to upgrade or make changes to the devices performing network access tasks, we don't necessarily need to change anything on devices performing application layer tasks. Common standard languages is another benefit, and that goes back to avoiding compatibility issues. In the example that I mentioned during the previous slide, I said that a Mac client computer can resolve names using a Microsoft DNS server. And that is because TCP/IP protocols define standard communication language. Devices from different vendors can communicate with each other at the same layer, so in our network, we can have a diversity of manufacturers even within the same layer. And lastly, having a layered model is a huge help in terms of improving and allowing protocols and technologies to evolve. And again, this is because changes at one layer does not mean that we need to have or to make changes at all other layers. So if we want to improve or release an evolved version of the protocols at a certain layer, that doesn't mean that we have to upgrade all layers at once. Improvements can be done independently at each layer. So now we know that the messages have to go through different layers of communication when they're traveling from source to destination. And as the message passes through the different layers of communication, the original message most likely will need to be broken into multiple pieces or multiple smaller messages And then at each layer, these messages will be encapsulated into layer-specific envelopes by adding layer-specific headers or trailers. And these header and trailers contain the information required for the message or the data to be handled properly and ultimately delivered to the intended destination. So the message takes different forms as it passes down the communication stack. And the output data unit produced by each network layer after including the layer-specific encapsulation is given different names at different layers. In general, we call them protocol data units, PDUs, but PDUs are given different names at different layers. So starting up at the application layer, the protocol data unit at the application layer is simply called data. So applications output data and they pass it down to the transport layer. Then the transport layer will take the data. It might have to break it down into multiple smaller pieces of data, and then it will include a transport layer header, transport header information. The result of this process produces what we call segments. So the PDU at the transport layer is called a segment. Then the internet layer takes segments from the transport layer. It will add its own layer-specific header information called the network header, and produces what we call a packet. So the output of the internet layer is called a packet. Then the data link layer, which is part of the network access layer in the TCP/IP model, will grab the packets and encapsulate them by adding header and trailer information. The data link layer actually places information before and after the data. And the PDU output by the data link layer is what we call a frame. Finally, the data link layer will pass down frames to the physical layer, and the physical layer is in charge of placing zeros and ones onto the transmission media. And that is why we call the PDU of the physical layer, we call it bits. So as the message is passed down, the communication stack is transformed from data to segment to packet to frame to bits. Just before, you heard me talk about the data link layer and the physical layer, and I was referring to the OSI layers that collectively perform the tasks performed by the network access layer of the TCP/IP model. So you might be wondering now, what are these OSI layers? OSI stands for Open System Interconnection, and the OSI reference model describes the functions of the communication process in a computer network. But this model breaks down the process into 7 layers rather than 4 as the TCP/IP model does. So the OSI model was developed by the International Organization for Standardization and the International Telecommunication Union, the ISO and the ITU. So in the early 70s, both the ISO and the ITU were working on similar models. Then in 1983, they joined them together and published what we know as the OSI model in 1984. So very much like the TCP/IP model, the functions at each OSI layer are defined without regard for the underlying infrastructure or technology. So the OSI layers are also independent from each other. And you will often hear the terms protocol model and reference model when talking about TCP/IP and OSI. So both OSI and TCP/IP are reference models and protocol models. TCP/IP describes the generic network functions at each of the 4 layers and is used as a reference to describe in general what needs to happen in an end-to-end communication process in a network. Now TCP/IP also defines a protocol suite, as you can see in the figure. It specifies a list of existing protocols that are to be implemented at each layer. And the same goes for the OSI model. There are actual implementations of the OSI model with protocols defined at each layer, but it's also used as a reference model for the generic networking process. So basically what this means is that if someone was to develop their own network protocols, they can have a look at the generic functions defined by the models as reference and then implement a new set of protocols that fulfill the same tasks. So both the TCP/IP model and the OSI model describe the functions and tasks to be performed in the network communication process. But TCP/IP groups these functions into 4 layers, whereas OSI groups these functions into 7 layers. And as you can see in these figures, the layers defined by TCP/IP can actually be mapped to the layers defined by the OSI reference model. The TCP/IP application layer performs the same functions collectively performed by the application, presentation, and session OSI layers. The transport layer and the network layer can be mapped one-to-one to the transport layer and the internet layer of the TCP/IP model, whereas the network access layer of the TCP/IP performs the task performed by the data link layer and the physical layer of the OSI model. One interesting fact is that you will find that the TCP/IP model layers are referred to only by name. We talked about application layer, transport layer, internet layer, network access layer. But when we're referring to the OSI model, we actually refer to them by their number. We talk about layer 1, layer 2, layer 3, and layer 4, etc. So when we say layer 2, we know we're talking about the data link layer of the OSI model. When we say layer 7, we're referring to the application layer. And this is a common fact. That's the way we refer to the layers of the OSI model. In this unit, we're going to focus our discussions and our lectures mainly on the layer 2, layer 3, and layer 4 layers of the OSI model. But we're also going to touch base on the application layer concepts as well as the physical layer concepts, which we're going to do on this lecture in the following slides. So the main function of the physical layer is to accept the frames coming from the data link layer and encode them into a series of bits, a series of zeros and ones, to get them ready for transmission over the physical media in the form of a stream of electric pulses or light pulses or radio waves. The signals, the type of signals that we use depend on the type of media that we're using to carry the information. So we will be using electrical pulses if we're using copper cables, or light pulses if we're using fiber cables, or radio waves if we're having a wireless communication. So the signals are placed onto the media one at a time. And at the receiver end, the receiver will read the physical layer at the receiver, will read the stream of signals from the media, and it will decode them back into their bit stream form and passed up to the data link layer as a whole frame. So what does encoding mean? So encoding means converting a stream of bits into a predefined code. For example, the Manchester coding defines that a change from high to low voltage in the signal represents a 0. And maybe I'm going to use my whiteboard to explain this. So in the Manchester encoding, if the signal goes from its low level up to the high level in the middle of the time period, then that represents a 1. Then if the signal goes from its high level to its low level in the middle of the time period, that represents a 0. And again, let's say that we need another 0, so the signal needs to be such that it goes from high to low in the next half of the time period. So that would be another 0. And then if we want a 1, we have to take the signal from its low level to its high level in the next half time period. That would be another 1 there. And this signal, if we were talking about voltage, for example, this could be 0 voltage, 5 voltage, or if we were talking about fiber, communication of fiber optics, this could be light. The high signal could be light, and no light could be the low signal. So that's what encoding means. So having a predefined code to signify the ones and the zeros in a physical signal. And the nature of the physical signal will depend on the type of media that we're using to transmit this signal. So encoding and signaling the data is two of the primary functions of the physical layer, where encoding means converting a stream of bits into a readable code, and the signaling means physically representing or choosing the nature of the signal that is going to represent a 1 or a 0 on the media. So the physical layer at the sending end will accept the frames from the data link layer and transmits them as binary bits over the media between the devices. And then at the receiving end, the physical layer will receive this signal on the media. It will convert it back into a sequence of bits, and it will pass it up to the data link layer as a whole frame. One of the fundamental principles of the physical layer is what we know as bandwidth, and this is the capacity of the medium to carry data. It is measured in bits per second, being the basic or the fundamental PDU of the physical layer. The bandwidth of the link depends on the physical properties of the medians and also the chosen signaling and encoding technologies. And then we have the throughput as another principle of the physical layer, which is different to the bandwidth. So the bandwidth is the capacity that the medium has to carry data, whereas throughput is the actual transmission rate at a given period of time. It does not usually match the medium capacity or the bandwidth, and this is due to several factors. So there are multiple streams of data going through the same link, and if there is higher amount of traffic, the throughput is going to be lower than when there is less amount of traffic. The throughput also depends on the type of traffic that is being transmitted. It's going to also be affected by the latency created by the processing of data over the multiple network devices the data crosses in the path. So overall throughput is the actual transmission rate, whereas bandwidth is the full capacity of the media to transmit data. There is another measurement other than bandwidth and throughput that is intrinsic to the physical layer and is known as a good put. And this refers to the transmission rate of usable data. So the actual data minus all of the overhead, the encapsulation, the acknowledgements, etc. So that is known as good put. And with this, we conclude this first lecture. Just as a summary, we covered network protocols, what they mean, what they're used for. We covered the TCP/IP layer architecture. We discussed the concept of data encapsulation, the benefits of using a layered architecture model. We discussed the purpose of a network reference architecture model. We also compared the OSI model to the TCP/IP model, and we briefly touched base on the physical layer by discussing the main purpose of the physical layer and the concepts of throughput, bandwidth, and